Hello everyone, welcome to the lecture series on IC applications. Myself Siva Ramakrishna, Department of ECE. In this lecture, we are going to discuss the applications of operational amplifier. Before we begin with the applications, we will look at the things what we have discussed so far regarding operational amplifier. So the session begins with brief recap of the things that we covered so far on operational amplifier. The key focus of this session is discussion on linear applications and non-linear applications. So in this lecture we discuss this particular concept, that is linear applications. What are the linear applications of operational amplifier? So before we begin the applications, we quickly recap the things that we covered so far regarding operational amplifier. We know the symbol. This is the symbol for operational amplifier, and this is the most important pin diagram or pin configuration of operational amplifier, where you can see 8 number of pins. IC741 is having 8 number of pins. This is an 8 pin IC. If you look at the diagram, you can see a notch. This is a symbol for the notch that represents that provides an idea where is the first pin and where is the last pin. To the left of this is going to be the first pin, and to the right of this pin is going to be the 8th pin. And what are the pins available in IC741, which is nothing but op amp. IC741 is nothing but op amp, operational amplifier. If you look at the pin diagram, the pin 1 represents input offset, so which we have seen, as the properties are one of the important parameter of operational amplifier. And pin number 2 represents inverting input, and pin number 3 represents non-inverting input. So if you look at the symbol for op amp, you may notice this is your input section, this is your input section, and this is the output. This is the output, so that we can easily represent in the symbol. So if you observe, there are two inputs. There are two inputs in the op amp. What are the two inputs? One is the inverting input and the other is non-inverting input. So as you know, inverting input represents the signal that is applied to this terminal will have a polarity of negative, will have a negative polarity. Whereas the signal provided across this at this non-inverting terminal will acquire a polarity of positive. That is, the signal will have a positive polarity which is applied to the non-inverting terminal, and the signal will have a negative polarity which is applied to the inverting terminal of operational amplifier. This is the input section. In the pin configuration, where do you find these two inputs? Where do you find these two input pins? That is, pin number 2 represents inverting input and pin number 3 represents non-inverting input. That is, if you want to provide excitation to the inverting terminal, we need to connect the signal from source to the pin number 2. If you want to provide excitation to the non-inverting terminal, we need to connect source to the non-inverting terminal, that is pin number 3. So do remember, pin number 2 and 3 represents or denotes the input terminals, where pin number 2 is for inverting input and 3 for non-inverting input. And if you remember, the operational amplifier has two bias voltages. What are they? So one is minus VCC and the other is, sorry, plus VCC and the other is minus VEE. We have two biasing voltages. So where do you find these two biasing voltages in the pin configuration? So if you observe, pin number 4 represents minus VCC. Don't worry about the minus VCC. It is nothing but negative polarity, negative bias. So pin number 4, at pin number 4, we need to provide negative bias. At pin number 4, you can remember like this. If you want to provide negative bias, that we can provide to the pin number 4. So this is nothing but negative bias. Pin number 4 is going to have negative bias. And pin number 5, we have another offset pin, that is nothing but input offset. So do remember, pin number 1 and 5 denotes the input offset. And coming to the pin number 6, so here you are going to get the output, actual output from this IC, right? Pin number 2 and 3 are responsible for the input and pin number 6 is for output. And coming to the pin number 7, so where we can provide the positive bias. So as we said, even in the symbol you can notice, so you will find two biasing voltages. One is the negative bias and the other is the positive bias, right? So negative bias is applied to the pin number 4 and positive bias is provided to the pin number 7. So here you will provide the positive bias of the required positive bias to the IC741, and pin number 7, no connection. So out of 8 pins in the pin configuration, 7 pins are under functioning. So of which pin number 1 and pin number 5 are for input offset, and pin number 2, 3 for input signal. Pin number 2, 3 are for input signal. So one is the inverting and another is non-inverting input. Pin number 6, we will get the actual output, the output of your IC741. And biasing across pin number 4 and 7, we will provide the required bias. Across pin number 4 and 7, we will provide the required bias. So this is the pin configuration of IC741. If you want to use this in the design of any electronic circuit, nothing but the applications, I am talking about the applications, one should follow this pin configuration. One should follow this particular pin configuration. So if you remember BJT, you will notice 3 terminals. In BJT, we have 3 terminals. What are the 3 terminals? If you remember, they are emitter, base and collector. So we need to provide the signal or wiring as per the circuit to these 3 terminals respectively without violating. That means if you are, suppose in the circuit you want to give the signal to the emitter, you cannot connect that to the collector terminal. You cannot treat them as, you should treat them as independent terminals. So this pin configuration should be remembered and understand as per the circuit configuration. As per the circuit configuration, one can provide these connections. Violation of any of these rules, that we stated here, the rules are nothing but pin configuration. If you have any violation, the immediate thing is the IC will stop working. That means it will easily get burned. That means IC will get burned. That means you just simply reverse the biasing. So strictly pin number 4, at pin number 4 we need to provide the negative bias. Suppose if you provide positive bias to the pin number 4 and negative bias to the pin number 7, what will happen? You are, due to some reason or unknowingly, you are interchanging these biasing terminals. So this will affect the functioning of the op-amp. So that will stop working and will burn so sensitive. So one should remember this pin configuration and follow accordingly as per the circuit configuration. And now we will recap the parameters of operational amplifiers. Operational amplifier both in the context of ideal as well as practical. So do remember, the ideal scenario is too far away from the practical scenario. It is always tough to meet the ideal conditions. It is always tough to meet the ideal parameters. Of course, one should consider what is the ideal value of so and so parameter. So if you look at the operational amplifier, so three most important parameters. What are they? One is the gain, input impedance and output impedance. What about the gain of operational amplifier in the ideal concept, in the ideal scenario as well as in the practical scenario? So try to remember, in ideal scenario it is always infinite. It is always infinite, and in the practical scenario gain is very high. We can say that for IC741, especially for IC741 I am talking, the gain will be, its actual value is 10 power 5, and in terms of decibels it will be 100 dB. Approximately you can say that one. And coming to the input impedance, so op-amp usually have a high input impedance that is nothing but infinite. It is infinite in the case of ideal situations. And coming to the practical situation, it will be very high, that is mega ohms. So one can expect a very high input impedance which is of the order of few mega ohms. At least it is going to be the 2 mega ohms. And coming to the output impedance, in the ideal situations it is very small. It is almost zero. In the ideal situations output impedance is 0, and in the practical situations it is very small but not 0. So that's what we said, no. So it is always tough to meet the ideal conditions, always tough to achieve the ideal values. So practical scenario is different and ideal scenario is different. But at least we can move the values close to the stated ideal values. So what we said, gain and input impedance are always infinite for a given IC741 in the context of ideal, and in practical scenario these values are going to be very high. Gain will be 10 power 5 and input impedance will be of the order of few mega ohms, and output impedance is 0 in the context of ideal scenario, and in practical scenario it is small but not 0, whose value will be 75 ohms. So these are the some standard values of IC741. One can remember the ideal context as well as practical context. So coming to the modes of operation. So this IC741 also can be operated in two modes. What are the two modes? One is the common mode and the other is differential mode. What is meant by the common mode? See, what is the important block in the operational amplifier? If you remember, it is nothing but a differential amplifier. What is the important block? It is nothing but a differential amplifier, where we have two transistors, that is Q1 and Q2. We have two transistors, Q1 and Q2. So both will have input section as well as the output section. Both will have the input section as well as the output sections, because we are using two transistors. And of course they are symmetrical, ideal in all the aspects, making of the similar material, everything is same. So coming to the common mode, what is meant by the common mode? Both the inputs are symmetrical or ideally same. Both the inputs are symmetrical or inputs also. The source signal that is applied to the transistors Q1 and Q2 is also same. That is for common mode. And coming to the differential mode, this differential mode excitation will can be done in two ways. One is a single-ended mode, single-ended operation, and the other is a double-ended operation. In the case of single-ended operation, so do remember what is the amplifier, what is the first stage of operational amplifier, means you should say that this is going to be the differential amplifier, right? So in the context of differential amplifier, we have two modes of operation. One is a common mode and the other is a differential mode. So in the common mode, both the amplifiers are going to have the similar excitation from the same source. We can say that they have similar value of input. And coming to the differential mode of operation, in the case of the single-ended, only one input is provided. Only one input is provided, that is among the two transistors. Either Q1 or Q2 will get the excitation. Either Q1 or Q2 will get the excitation. What about the other transistor? That remains ground. The other transistor will never get any excitation. Ideally speaking, that will be grounded. So that is called single-ended. And in the case of the double-ended, both the transistors will have their own excitation, but it is in terms of the polarity. So one is the positive polarity and the other will be the negative polarity. At least there is a difference in terms of the polarity. So that means to the Q1, if you are giving plus 10 volts, Q2 will get minus 10 volts. This is called double-ended operation of the differential mode. So in double-ended, both the transistors will get the excitation. Excitation in the sense both the transistors will get the input. They differ in terms of their polarity. If one transistor gets a positive polarity input and the other will get the negative polarity input, that is Q1 will get a positive signal and Q2 will get a negative polarity signal. That is called double-ended. In single-ended, it is very clear. Only one transistor will get the excitation and the other transistor is connected to the ground. This is called common mode as well as a differential mode operation. And if you remember, the most important parameters to be remember are considered in the operation of your IC741 is common mode rejection ratio. Since we have two modes of operations for op-amp, one is a common mode as well as a differential mode. This common mode signal must be as small as possible, whereas a differential signal will be very high. That is, gain of the differential amplifier in the common mode should be very small when compared to the gain of this differential amplifier in differential mode. That is what we need to say. AD must be very, very large than your AC. AD should be very high when compared to the common mode signal AC. So what is the meaning here? This common mode rejection ratio must be very high for satisfactory operation of the operational amplifier. So this is called common mode as well as a differential mode operation of IC741. And the other parameters what we discussed for operational amplifier, they also applicable to the IC741. What are the parameters we said? If you remember, they are nothing but the open loop voltage gain, maximum output voltage swing, and the other is input offset voltage, input bias current, input offset current, and slew rate. These are the standard parameters. These are the standard parameters of operational amplifier. We quickly recap these parameters also. So what is the first one? Open loop voltage gain. It's a voltage gain. It's a voltage gain under open loop conditions. So what is meant by the gain here? It is nothing but the ratio between output voltage to the input voltage, under open loop condition. So open loop means there is no feedback path between the output and input ports. And the next one is the maximum output voltage swing. So what is meant by the maximum output voltage swing? See, when there is no input applied, across the input terminals, what is the ideal value of the output? When no input, ideal value of the output should be 0, right? If input is provided, what should be the maximum output voltage? That should be equal to the VCC, nothing but positive biasing, nothing but the biasing input. Okay, that is nothing but the maximum output voltage swing. Ideally, this output should be equal to VCC, but it should be at least approximate to that of your VCC. So what is by the maximum output voltage swing? Under no input conditions, ideally output will remain 0. If we provide input, the output is expected to have a swing. That is nothing but the maximum value of the output will be approximately equal to the VCC. Right, and next one is the input offset voltage. What is meant by the input offset voltage? Again, when zero input, output should be 0. Practically, this situation will never happen. Ideally, see, we can always compare ideal versus practical situations, but ideally it is very tough. Meeting the parameters that we define ideally is always tough. So that's what we are going to say. Ideally, when there is no input, output should be 0. Practically, what about the practical? In practical situations, we get small error voltage. Small error voltage, that is called the offset voltage. It is unavoidable. Even under zero input conditions, one can get a very small output voltage. That is nothing but the offset voltage. And input bias current. What is meant by the bias current? It is the bias provided to the base of your amplifier. That is differential amplifier. Right, bias current applied for proper biasing. That is because we are going to operate the amplifiers. We are going to operate the transistors for differential amplifier context, in the context of differential amplifier. So transistor needs to be operated in so and so region, nothing but the active region, to behave like an amplifier. Right? We need to provide some satisfactory biasing values, nothing but the biasing current, which is called as the input biasing current. And similarly, we have input offset current. This is very similar to the previous one. What we said, ideally two input currents are same. The difference will be 0 because we have two transistors, right? Two input currents are going to be the same. When both are same, ideal case, in the ideal situation, there will be 0 current at the output. But practically what happened? There is a slight difference between them. This difference is called the input offset current. And the last parameter is nothing but the slew rate. So another important parameter. So do remember CMRR and the slew rate are very, very important in the context of your operational amplifier. CMRR should be high. High means differential gain AD should be as high as possible when compared to your common mode gain. Differential gain should be very high when compared to the common mode gain. Similarly, what is the slew rate here? This is nothing but the rate of change of output voltage for a fractional change in your input voltage. So we have seen maximum rate of change of output signal with respect to the change in input signal is called the slew rate. So these are the parameters of IC741 operational amplifier. Before we begin with the working of IC741, one should familiarize with all these basic concepts. These are fundamentals that will help you to understand the operation of IC741 much better way. Now we begin the applications. These applications are broadly categorized into two types. The op-amp applications are categorized into two types. One is the linear and another one is a non-linear. That is, we have both linear applications as well as non-linear applications. So these are the two applications. This is a broad classification of operational amplifiers. Now we will see what are the linear applications of IC741. If you remember, the first one is going to be the inverting amplifier, and the second is non-inverting amplifier. Third application, voltage follower, and the fourth is logarithmic and anti-logarithmic amplifiers. Similarly, we have instrumentation amplifier, integrator using differential amplifier using operational amplifier, and finally it is going to the differentiator. These are the applications of IC741 or op-amp. What type of applications are they? They are going to be the linear applications. They are called linear applications of operational amplifiers. You will see why they are called linear and what are non-linear applications. So by the time when we conclude non-linear applications of operational amplifiers, you will get a clear picture. What is the difference between linear application and non-linear application? What are linear and non-linear applications of a differential amplifier? These things you will get familiarized by the time when we close the discussion on non-linear applications of IC741, right? So if you see the list, we have 7 applications. We need to discuss all these 7. First, we begin with inverting amplifier. In all these set of applications, so you need to understand the basic operation of the operational amplifier. That is how we are considering the operational amplifier. So do remember all the 8 pins. How we are using all these 8 pins to achieve these set of applications. How we are using the 8 pins in IC741. 8 pins in the IC741. That is operational amplifier. So look at the basic circuit diagram of inverting amplifier. See, the term itself giving some idea. So what it is an amplifier. So what we are going to say here, we are going to design an amplifier. What type of amplifier it is? It is nothing but inverting. Amplifier. So the first application is nothing but the amplifier. What type of amplifier it is? It is inverting amplifier. Now consider IC741 operational amplifier. Look at the circuit configuration. As usual, we have inverting terminal as well as the non-inverting terminal. It is inverting amplifier. So what we can do? The non-inverting terminal is connected to ground. That is the first step. And then wherever we have the inverting terminal, there we need to provide the excitation. Nothing but the input. That is, input is connected to the inverting terminal of IC741 or operational amplifier. And as you have you might familiar. So we cannot provide the input directly to the device. So that you have seen even in the transistor raised amplifier. Suppose you are working with the common emitter configuration. Input is provided to the base. How we are giving the source? Through some resistance. So here also we are using some resistance. So let us say RA. That is nothing but the input resistance, right? And then there is a feedback resistance. This is called a feedback resistance. What is the value there? It is RF. This is called a feedback resistance, which is RF connected between the output and input, right? So this is a very simple circuit. So how we design the circuit here? This is inverting amplifier. So the non-inverting terminal is ground. No input or no excitation to the non-inverting terminal. And input terminal is getting excitation. That is, we are providing some source signal or input signal to the inverting terminal through some input resistance, which is RA. And then there is a feedback resistance that is connected. This is for stability. Okay, why we are connecting this RF means, see, op-amp will have a good stability. That is again another property of the operational amplifier. So we have a feedback resistance, which is RF. RF is connected between the output port as well as the input port, right? And now what we are going to determine here? We are going to determine the gain. Of the operational amplifier. Gain of the inverting amplifier. What is the gain here? It is nothing but the output voltage to the input voltage. It is the ratio of output voltage and input voltage. Now see here, we consider the current in this particular input section. What is I here? What is current I here? One can say that it is nothing but V in minus V out. It is V in minus V out by the total resistance is nothing but Ri plus Rf. That is V in minus V out by Ri plus Rf. Okay. And now if you consider the equivalent circuit, of this inverting amplifier, what it says here, so we have an input signal here and we have output signal. And here is your op amp. This is the equivalent circuit what I am presenting here. So here we have a V2. We have a voltage called V2. So which is at virtual ground. Because the other terminal, when the other input terminal is connected to the ground, the other terminal also behaves like a virtual ground. Nothing but V2. Right, V1 is input. Here we can say that this is V in and this is your R input voltage and this is your RF, and here we have V out. So what I mean to say, so we have two input terminals. If any of the input terminal is connected to the ground, other terminal also at virtual ground. Now what happened in the case of inverting amplifier? Non-inverting input is connected to the ground. So the other inverting input is also at virtual ground. So we have V2 equal to 0. From this circuit, how can I say I can say I equals to, the current I is equals to, I can write I is equals to V in minus V2. I can say V in minus V2 by R in, right? Also, this is equal to V2 minus V out. So this is what I equals to V in minus V2 by R in, and this is also equal to V2 minus V out by RF. Okay. So now if we simplify this expression, what we are going to have here, we just see here, we have V in minus V2 by R in and V2 minus V out by RF. So how can I write this one? V in by R in minus V2 by R in, which is equals to V2 by RF minus V out by RF, right? Now what we can do, move the V2 components to the other side. So what we will get here? V in by R in. So we can say that V in by R in is equals to, so we can take V2 as common. Once we shift this V2 by R into other side and take V2 as common, so we will get V2 into 1 by R in plus RF, minus V out by RF. So this is what we are getting. Okay. And now what is the value of V2? So this is 0. The value of V2 is 0. V2 is nothing but at the virtual ground. So if you substitute the value of V2, that is 0 here, what we will get now? We can say that V in by R in is equals to V2 by RF. So what we can get here? If you substitute V2 as 0 in this equation, we will get V in by R in is equals to V out by RF. Now what we need to determine? Gain. Gain is nothing but V out by V in. So perform cross multiplication. So what we will get here? By doing cross multiplication, we will get the gain of the inverting amplifier. Gain of inverting amplifier is V out by V in is equals to V out by RF by Rin. The gain is equals to the gain of inverting amplifier is RF by Rin, where RF is feedback resistance, this one, and Rin is the amount of input resistance connected to the input terminals. So this is called inverting amplifier. And now we will move to the other application. which is a non-inverting amplifier. So again what it says, it is also an amplifier. Also an amplifier. What type of amplifier it is? Non-inverting amplifier. So which means the inverting terminal, this is connected to the inverting terminal, this is the inverting terminal which is connected to the ground. The inverting terminal is connected to the ground, whereas a non-inverting terminal, this is called a non-inverting. This is called non-inverting terminal, and this is your inverting. The non-inverting terminal is connected to the signal source Vin. Input is provided to the plus. There is nothing but the non-inverting terminal, whereas inverting terminal is connected to the ground. And similarly, this is the equivalent circuit. Equivalent circuit of your non-inverting amplifier. So let us determine the gain of non-inverting amplifier. So similar situation we have. See, you can find V1. So from this circuit, by using the voltage division rule, you can find the V1, the expression for V1. How can I write V1 here? V1 is equals to R2 by R2 plus RF into Vout. That is the total resistance. R2 by total resistance. What is the total resistance? In the network we have R2 plus RF into output voltage Vout. This we can call it as the V1. Okay. And so what is V1? Nothing but the input applied to the non-inverting terminal. Input applied to the non-inverting terminal. So this is nothing but Vin. So what is Vin now? It is very straightforward this time. Vin is equals to R2 by R2 plus RF into Vout. Okay. Now what is the gain here? We need to calculate the gain of non-inverting amplifier. So again perform cross multiplication. What we will get? Vout by Vin is equals to, we will get R2 plus RF by R2. So we can write this fraction into two terms. So how can I write R2 by R2 plus, that is RF by R2. So R2 will go out and we left with 1 plus RF by R2. It is nothing but 1 plus RF by R2, which is the gain of non-inverting amplifier. Which is the gain of non-inverting amplifier. So you can find, you can remember these two expressions quite useful while solving some numerical examples. There is a gain of inverting amplifier, as well as a gain of non-inverting amplifier. So gain of non-inverting amplifier is RF by R2, and gain of inverting amplifier is RF by Rn. RF by Rn is the gain of inverting amplifier, and gain of non-inverting amplifier is 1 plus RF by R2. You can say there is nothing but here it is the resistance connected in the circuit. So there is a slight difference in the circuit arrangement for non-inverting amplifier. So here we are going to provide the feedback path. This forms a potential divider network between the output as well as the input as well as the inverting terminal. So this is the circuit what we have considered here. So we are getting the gain expression, that is 1 plus RF by R2. So these are the few examples of linear applications of IC741 operational amplifier. In the next class we will continue the other applications. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.